Hey everyone, welcome to The Explainer. Today, we're diving headfirst into the incredibly high-stakes world of anomaly detection. Imagine for a second, a credit card being used to buy coffee in New York at 2 p.m., and then, suddenly, trying to buy a TV in Tokyo at 2:05 p.m. Or picture a factory sensor that randomly spikes to 150 degrees when its absolute strict normal range is 80 to 120. Finding these anomalies? It's absolutely crucial. I mean, we are constantly on the hunt for things like network intrusions, catastrophic equipment failures, and massive fraud rings. And the cost of missing them is staggering. We're talking billions in lost revenue, massive operational downtime, and stolen data. But, as it turns out, actually finding these threats is a whole lot harder than it sounds.
And here's the core problem staring us right in the face. Fraud, for example, often makes up just 0.1% of all transactions. Equipment failures? They might literally only happen a handful of times a year. This exposes a pretty fatal flaw in standard machine learning, which is, you simply can't train a traditional classifier on something that almost never happens, right? A standard model needs to see thousands of examples of an anomaly class to learn what it looks like, but in the real world, there's practically nothing in that anomaly class to learn from. Plus, even if you do somehow scrape together a few labeled examples, tomorrow's fraud scheme is pretty much guaranteed to look completely different from today's.
Okay, let's dive into this, because this is really the central mystery of our explainer. How exactly are we supposed to detect tomorrow's novel, totally never-before-seen anomalies, when literally all the data we have is just for today's totally normal behavior?
To solve this puzzle, here's our roadmap for today. First, finding the abnormal. Second, modeling the normal. Third, we're going to peek under the hood of 4 detection methods. Fourth, we'll build a detection pipeline. And finally, we'll wrap up with the business decision. Let's get right into it.
Starting off with Section 1, finding the abnormal and identifying the actual threat.
You know, it's often said that normal is incredibly easy to define, while abnormal is, well, just whatever doesn't fit. But not all anomalies are created equal. There are really 3 distinct types of threats we need to keep on our radar. First up, we have point anomalies. This is a single data point that's just weird, completely regardless of the surrounding context. Think of a single $50,000 transaction from a checking account that historically only ever spends $50 at a time. That immediately sets off alarm bells, right? Second, we have contextual anomalies. Here, the value is unusual only given its specific context. Like, 90 degrees is totally normal in the middle of summer, but it's highly anomalous in the dead of winter. And finally, collective anomalies. This is a sequence of data points that's unusual as a group, even if each individual point on its own seems totally fine. One failed password login? Totally normal. We all forget our passwords. But 50 failed logins in a row? Yeah, that's a clear brute force attack. Now, most basic methods we use really only detect those point anomalies. So to catch the contextual and collective threats, we have to start relying pretty heavily on sequence, time, or location features.
Which brings us to Section 2, modeling the normal, and what I like to call the paradigm shift.
And this brilliantly illustrates where we undergo a massive mental shift. Think of this as the jujitsu of data science. We're literally going to use the weight of the problem against itself by flipping it entirely on its head. Let's look at the trade-off between these two approaches. If you treat this like a standard supervised classification problem, you're basically trying to memorize exactly what every possible anomaly looks like. And sure, that gives you high precision on the exact types of anomalies you've seen before, but it completely misses novel types. You're fighting a losing battle against an ever-changing enemy. But with unsupervised detection, instead of trying to learn what's abnormal, we just learn what normal looks like. We map out the safe zone. Then anything that deviates from normal is inherently suspicious. This catches novel, totally never-before-seen deviations without needing a single labeled example. The catch? Well, you do get a higher false positive rate, mostly because not everything unusual is necessarily a malicious threat.
All right, Section 3, 4 detection methods. Let's look under the hood.
The absolute simplest approach here is the z-score method. Basically, it computes the mean and the standard deviation of each feature and then flags any point that falls more than, say, 3.0 standard deviations away. In a beautifully perfect, normal Gaussian distribution, 99.7% of your data falls within that safe range. It's blazing fast to compute and incredibly interpretable, but it has a fatal weakness. It assumes your data is normally distributed. If you have skewed data, like transaction amounts where $1,000 is rare but not necessarily anomalous, or multimodal distributions, think of a restaurant that has a massive lunch rush, huge dinner rush, but it's completely dead in the afternoon, the z-score just completely falls apart.
So, to fix that vulnerability, we can step up to the IQR, or Interquartile Range method. Instead of the mean, this looks at the middle 50% of your data.
The default factor here is 1.5, which practically acts like the whiskers on a box plot. Any point sitting completely outside those whiskers gets flagged as a potential outlier. And the beauty of this is that percentiles aren't skewed by extreme values, so it's far more robust than the z-score, and it absolutely doesn't require your data to be perfectly bell-shaped.
Now, what's really interesting here is how isolation forest entirely changes the game. This method operates on a really brilliant insight. Anomalies are few and different. So if you start randomly cutting up your data, just picking random features and random split values, normal points, which live in these dense, packed neighborhoods, take a ton of splits to isolate. They're huddled tightly together. But anomalies? They live way out in the sparse woods. It only takes 1 or 2 random cuts to isolate them completely. The anomaly score is simply based on how short the path length is to isolate a point. It scales beautifully to massive datasets and requires literally 0 assumptions about your data's underlying distribution.
But wait, what if an anomaly isn't globally weird, just locally weird? Enter Local Outlier Factor, or LOF. This method finds the nearest neighbors of a point and compares their densities. Imagine a sparse cluster of 50 points sitting right next to a super dense cluster of 1,000 points. A point on the edge of that sparse cluster isn't really globally unusual when you look at the whole dataset, but it is highly locally unusual if its immediate neighbors are way denser than it is. LOF is amazing because it captures that incredible nuance that global methods completely miss, finding those localized anomalies just hiding on the very edges of our data structures.
So let's quickly summarize these 4 tools. When comparing their strengths and weaknesses, z-score and IQR are lightning fast, but they miss local anomalies completely. Isolation forest is fast, scales remarkably well, and handles high dimensions wonderfully. LOF, it's brilliant for local anomalies, but runs incredibly slow and really struggles when you throw too many dimensions at it. Because their assumptions and computational speeds make them suitable for totally different tasks, in practice, the most powerful approach is an ensemble method. If you normalize their scores and just average them out, a point flagged by all 4 methods is almost certainly a severe anomaly, which significantly reduces your false positives.
Moving on to Section 4, the detection pipeline, going from theory to production. Okay, so we've got the math down. Now, let's see how this actually breathes in a real, live production environment through 6 critical steps. First, you collect your baseline data during a period of known normal behavior. Then, feature engineering. And remember, raw features are rarely enough. You're going to need rolling statistics, ratios, domain-specific features like calculating the exact time since a user's last login, or maybe the acceleration rate of a temperature change. Third, you train the detector to thoroughly learn the shape of normal. Fourth, you score new data as it comes in live. Fifth, you set a threshold and trigger an alert when it's crossed. And finally, step 6, feedback collection. When human operators investigate these alerts, that feedback is absolutely essential to tune the system. Honestly, if you skip this, you're going to trigger massive alert fatigue, and operators will just start ignoring your system entirely. Nobody wants that.
Finally, Section 5, the business decision, cost and context. We're taking all this math and bringing it right back down to the human element and actual business reality. I want to highlight a really crucial concept here. Choosing a threshold is a business decision. It's not a technical one. The math gives you a continuous anomaly score, maybe a 0.82 or a 0.95. It tells you exactly how weird something is. But out in the real world, we humans need a binary decision. Do we block this transaction? Yes or no? Do we completely shut down the factory line? Yes or no? The algorithms literally cannot answer that for you. That requires real human context.
So the crucial point is really seeing the massive contrast between different real-world scenarios. Take fraud detection. Missing a fraudulent charge absolutely destroys customer trust, but a false alarm? That just costs a fraud analyst maybe 5 minutes to review. So you set a very low threshold, you catch way more fraud, and you gladly accept those false alarms as a standard cost of doing business. But for equipment maintenance, a false alarm means an unnecessary factory shutdown costing $50,000. Meanwhile, a missed failure is a $500,000 catastrophic repair. So you set a much higher threshold here. The optimal threshold entirely depends on the true cost ratio of false positives to false negatives for your specific business.
Now, the absolute biggest mistake you can make is assuming your work is done once the model is initially deployed. Actually, let me rephrase that. Anomaly detection is a living system. It is not a one-time model. Out in the real world, data distributions constantly shift. Consumer behavior fundamentally changes over time. Mechanical equipment progressively ages. And all of this creates massive threshold drift. What was considered a perfectly calibrated anomaly score yesterday might be completely, utterly useless tomorrow. Operators have to continuously monitor the score distributions and dynamically tune the entire system,
based on ongoing real-world feedback.
So I'll leave you with this somewhat provocative thought to ponder. As your data distribution inevitably shifts tomorrow, will your definition of normal shift with it? Building an anomaly detector isn't just about learning the haystack once, it's about continuously studying how that haystack changes in the wind. Thank you so much for joining me for this explainer. Keep asking the big questions, and I'll catch you next time.